examples. And Regina has done a lot of work in enlargements and this area, and so I'm expecting she's got a lot to say here, so I'm looking forward to this.
Okay, so thank you very much for everybody for your patience of listening to me for 2 hours. And I hope that I will deserve your attention. So this tutorial, I really want it to be like a tutorial, right? So just think of yourself as a student, as a very good student, which can ask very good questions to a very bad teacher. So please feel free to interrupt me at any point, because the objective of this hour is not to show you the things without any logic or without any order, but to make sure that you take home some concepts related with maximally monotone operators. And if you did not know anything about these objects before, at least you will get some flavor of what it involves and whether you would be interested in doing something in this topic. So I will start by mentioning the very, very basics, and please feel absolutely free to stop me. The more you stop me, the better, because I will have the idea that you are following what I say. And I would really want many people, especially the young people, or especially the people who started to look at optimization or no-smooth analysis now, to tell you that there is so much to do, and it's such a fascinating place to be when you go to maximally monotone operators. And the bridge that I want to show you is, again, going back to my talk in the morning about the link between maximal monotonicity and convexity. But I will start mentioning what are maximally monotone operators and why they matter. So this part has to do with an arbitrary point-to-set map. And in this talk, the setting will be, everything will be in Rn, right? So I want to keep things simple and clear. So what is a point-to-set map? A point-to-set map maps a point x to a set T of x. So this is now a subset of Rn. So a set can be empty or not empty. Being empty is not good. Being not empty is good in point-to-set analysis. And when a set is not empty, then you are standing in the domain of the map. And what is the range? The range are those V that belong to some T of x for some x for which, of course, T of x is not empty. So here, these are the logical replacements from the classical analysis to point-to-set analysis. So the domain is wherever the map is not empty. The range is whatever the point the map reaches via some x in the domain. And the graph is a combination of these two in a very particular way. So for every x in the domain and v in T of the same x, you take all those vectors, all those pairs xv. And this, of course, generalizes the classical definition of x f of x of the classical definition that you see in calculus 1. But a nice property that you have in point-to-set is something that doesn't hold usually for an arbitrary point-to-point function, is that you can always define the inverse, right? So you know that in point-to-point analysis, you can only define the inverse when you have some kind of bijective relationship. But in this case, no matter who is your point-to-set map, you can always define the inverse as those x's for which, of course, x is going to be in the domain by force of the definition, but of those x's in the domain such that v is in T of x. So in fact, the graph of T minus 1 is somehow the same as the graph of T, but with the variables swapped from their place. And it's very interesting for us to look at the graph of T, because all the variational problems that are of interest happen in this set graph of T. So when we want to find the zero of T, or when you want to solve an optimality condition, you want to solve a very particular pair in the graph of the operator. Okay, so what we have seen until now were definitions that concern every point to set map. So what happens when we know a little bit more about these maps? So maximally monotone operator is an operator that satisfies a property of monotonicity. So this means that when you take the difference between two elements in the domain and you multiply them by using the scalar product, you multiply by the increment in the codomain, the corresponding increment. So here, y star is not any y star should be in T of y, and x star should be in T of x. So these are pairs in the graph. Then this product should be monotone. So note that this is a restriction in the graph. Not everybody can be in the graph of this guy's T. Only you can have a point in the graph if you satisfy this inequality. So this is a restriction of the graph. So how much can we restrict? So we try to see what is the maximal set that we can use that will still satisfy this restriction of the graph. So you start to add points so that you can, so suppose that you have this thing here and this thing here, and so you can add this piece without destroying the monotonicity, but you can go all the way and add all the parts without destroying the monotonicity, and you cannot go further, because if you go further, you destroy the monotonicity. So the idea is that how far can you go adding guys into this graph without destroying this monotonicity property? So you will get a very big graph, and that graph will be the graph of a maximally monotone operator. And that's the reason for which this is called maximally monotone, because it's maximal with respect to the monotonicity property. So these operators are very important. So besides from being models for fundamental problems in variational analysis, they also have very nice properties. You can operate them in a nice way. So for example, if you take a non-negative multiple, you are still monotone. And you take the sum of two monotone operators, you are still monotone. Not necessarily maximally monotone. So if you take two operators which are maximally monotone, you need some kind of overlap between their domains in order to be able to conclude that the sum of these two guys is going to be maximally monotone. And one idea for which, one idea that tells you that this is not going to be a trivial situation is because you know that the Minkowski sum of two sets, so if you have two sets A plus B, the Minkowski sum is just the set AB such that A is in A and B is in B. So this is the Minkowski sum of two sets. And when these two sets are closed, not necessarily the Minkowski sum is going to be closed, right? So this is somehow behind the non-triviality of this conclusion. But I don't want to get too technical. So if you are in Rn, then when you have a maximally monotone operator T, then a non-negative multiple will be maximally monotone, and the inverse will also be maximally monotone. So this is very nice, and it is holding because of the reflexivity of the space. And another issue is that important sets that you may want to compute, so in cases you may want to compute the inverse image of zero. So these are the zeros of the operator. The zeros of the operator are your target, are the guys that you want to compute. These guys have a nice properties. if T is maximally monotone. This set is a closed and convex set. So this is an important property. And if A is a matrix, not necessarily symmetric, an affine map is maximally monotone if and only if you have A of x times x non-negative. So remember that A is not necessarily symmetric. So this is what an affine maximally monotone operator looks like. So it's some kind of extension of positive semi-definite matrices, etc. And what about the continuity properties? What can we say about the continuity properties of this operator? I want to keep things simple. So in the point-to-set mappings, you have essentially two ways of looking at continuity. Because when sets come into play, there are many ways in which you can extend the classical idea of continuity. So what is the classical idea of continuity for the point-to-point case? So what was Cauchy's concept of continuity? Cauchy's concept of continuity was that you can draw your graph of your function without lifting the pen. That's Cauchy's idea. But topologically speaking, this means that the graph is a closed subset of the product of Rn times Rn. So this set is closed. This is one primitive idea of continuity. And that primitive idea survives in the case of point-to-set maps. So one of the main concepts of continuity, which is called outer semi-continuity of a point-to-set map, and not necessarily maximally monotone, any point-to-set map is said to be outer semi-continuous if and only if the graph is closed, right? And what happens is that the maximality of maximal monotone operators tells you that the graph is going to be closed. So the maximality implies the outer semi-continuity. So this is something that automatically holds for every maximally monotone operator. That tells you that these operators are nice from that point of view. But there's another point of view, which is also very important. As I was telling you, an important problem to solve is this one, 0 in T of x. So the idea is that you don't want any guy in T of x. You want the guy in T of x that satisfies that 0 is in T of x. So you want 0 in T of x. So you don't want anybody else in T of x. You don't want to hear about it. And this is something that unfortunately for maximally monotone operators doesn't happen unless T is point-to-point, unless T of x is a point. In fact, that corresponds to the concept of continuity called inner semi-continuity. A point-to-set map, any point-to-set map is inner semi-continuous at x if for every v in T of x, and here this is the important part of the definition, no matter who is the v in T of x, and no matter who is the sequence xk converging to x, you will be able to find a sequence xk vk in the graph of T such that the vk guys converge to your original selected v. And this is very important because suppose that you have this problem with this function, it's a very simple function, continuous, the modulus, right? What is the subdifferential of the modulus? The subdifferential of the modulus is, so the modulus is this function. So if x is non-negative, the derivative is 1. If x is negative, the derivative is -1. But if x is 0, the derivative is any tangent that goes from -1 to 1. So what is the derivative is a tangent to the graph, right? So how many tangents can you draw to this graph at 0? Well, you can draw infinite number of tangents going from -1 to 1. This means that the subdifferential is going to be the whole interval minus 1, 1 when your point, when your reference point is 0. So this means that the subdifferential, the graph of the subdifferential is this, right? Now what happens here? You want to find your minimum of this function, and your minimum, of course, is here at 0. So when you take any sequence of tk's that converge to 0, either you will get minus 1 as an image, or you will get 1 as an image of your gradient. You will never get something that gets even closer to 0, right? Because you have to converge through points in the graph. When you converge through points in the graph, every accumulation point of this part of the graph will be here, will be the point 0, 1, or every accumulation point of the graph in this region will be 0, minus 1. So you will never get to 0, 0, which is that pair that you are looking for in the graph of this simple, very simple function, right? So this is a pathology, I could say, or we can call it a defect, not a nice feature of a maximally monotone operator. And we will see that enlargements come to help, because enlargement will give you an approximation of the graph of any maximally monotone operator in such a way that every enlargement is going to be inner semi-continuous at x, right? So this is one advantages of enlargement. Now, just this is
Regina, there's actually a question in the chat.
Yes.
The question says regarding, it's from Juan. She says regarding item 2, is the maximally monotone operator that has continuous single value selection.
Okay, so sorry. Yes, Hoa. Look, if the result is as follows: T is going to be inner semi-continuous at x if and only if T of x is a singleton, a single element. So every operator has a single value selection, right? So you can always select a guy by using Zorn's lemma or by using some other rule. You can always have a single value selection. However, if you really want your operator to be inner semi-continuous, you have to have T of x equal a single point. Because if T of x, like here, T of x is a whole interval minus 1, 1, right? And the operator is not going to be inner semi-continuous at this point, no matter what you do to it. Because the monotonicity is restricting the format of the graph. You cannot come to the graph via these directions here because of the monotonicity property that you are imposing, right? So because if these guys belong to the graph of T, then T is no longer monotone. You see where the problem lies. So the monotonicity precludes the graph from being inner semi-continuous unless T of x is a single point and you have an only. So for example, here your image is a single point and you have a unique way of approaching it via the graph. You can do it. And because you can, it's somehow approachable via points in the graph, then you can have that point. So look, if you have here, the only way to approach via the graph is through here. But then you are already there. You're already in the set where 0 is. So every algorithm will stop as soon as you are here or here. As soon as you are here, your algorithm will automatically stop because you got to a point where 0 is in T of x, right? But that is not helpful for you Okay, but that's not helpful for you. Why is not helpful? Because it doesn't tell you that you arrived at the solution, because your second coordinate is -1. It's not 0, right? So you don't know whether you are in a solution or not. I don't know if this answers
Thank
your
you.
question.
Thank you, Regina.
Okay, but thank you for your question. Yes, Alex.
Go ahead.
Sorry, maybe I'm also missing something here. Take T of x equals the whole space everywhere. Is it in a semi-continuous?
Yes.
So
It's
it
the whole
doesn't have to be
space.
single valued.
No, but for that case, because T is not monotone. T of x, so okay, T of x is the single, is Rn for every x, right? So the graph of your operator is this. So for every element in the graph, you can approach it in many ways via points in the graph. But if your operator is forced to be monotone like this, so this is your graph here, and you have a point here
Okay.
that
This
you want to
slide is
approach.
only for MM operators. I see. Sorry. Thank you.
Yes,
Thank you, Regina.
yes, but this definition is for point to set, and this definition is for point to set. So these definitions are all point to set. But what I'm trying to pass in this slide is the fact that if T is maximally monotone, then what can you say in terms of point to set continuity properties? Well, you can say that it's going to have a closed graph because of the maximality, and you're going to be able to say that it's not going to be inner semi-continuous unless T of x is a singleton. Okay, so there is a comment by Julian that says generally when T is constant. Yes, of course. If T is constant, then every point in the graph can be approached by other points in the graph. Yes. Okay, so let's go. I'm happy that this is generating some questions, because it's really making me even look at these definitions in a new and different way. And this is just wanted to mention what the curve of a point to set mapping, which is maximally monotone, looks like. So it's going to be an increasing curve with no holes. And these parts here, these vertical parts, are going to be the point to set regions where the function is not going to be inner semi-continuous. So for example, how do you see this outer semi-continuity in pictures? So this operator here is monotone, but it's not maximal, because you can still add some guys, and you have many ways of adding these guys. So in this case, you have a single way of adding them, but in this case, you can add it in as any ways you can, just preserving the monotonicity, right? So this gives you an idea, at least for functions from R to R, how these maximally monotone operators look like. And I suppose I told you that the maximally monotone operators are important, and I mentioned many cases in which these problems involving maximally monotone operators arise, of course, in optimality conditions where T is the gradient and the point Z is 0. You can show also that fixed point problems are equivalent. So the fixed points of the resolvent, so if you call this operator the resolvent of T, where lambda is positive, so this is the resolvent. So every fixed point of the resolvent corresponds to the 0 of T. So fixed point problems are inherently connected with inclusion, this type of inclusion problems. And of course, variational inequalities, which were my first lab in mathematics. My first lab was variational inequalities. So a variational inequality involves a maximally monotone operator T0 and the normal cone to a set C. So suppose that you have a set C. What is the normal cone of C at the point X? These are all the directions that point outward the set with respect to all the directions that point inward. So you form an obtuse angle, and therefore the angle of the product, the value of the product is going to be negative. So this is called the normal cone operator because it gives you all the directions that point outward from a given point at the boundary of the set. And in the interior of the set, this normal cone is identically equal to 0, right? Because only W equal to 0 can form a negative angle with every single direction in the space. So the variational inequality problem corresponds to finding a 0 of the sum of two operators, one of them being the normal cone associated with C. And it can be written in terms of inequalities in this way. So this really implies that you have a 0 of this inclusion. And this is totally written in terms of maximally monotone operators. But as I have told you, if you want to solve these methods, or if you want to generate, if you want to solve these problems, and you want to generate convergence sequences that converge, or if you want to define a sequence that converges to a solution of these problems, you need this operator to have good continuity properties. You need this operator to have a closed graph, and also you may need some inner semi-continuity properties. Those are also important in convergence analysis. And this means that you may want to approach the graph of your operator by some other point to set map, which has that inner semi-continuity property that you look for when you devise methods for solving these problems. And this is where enlargements come to be. So what is an enlargement of a given maximally monotone operator T? So from now on, T is a fixed maximally monotone operator. And an enlargement, of course, you need to have some measure of how good is your enlargement. When you enlarge something, you need to have some measure of accuracy for your enlargement, how accurate your approximation is. And we will measure this accuracy by using a non-negative parameter, epsilon. So this means that our enlargement is a function not only of the domain of the operator, because it should be applied to the same points as our operator is applied to, but also it should be a function of how close we are to the original operator. So in general, it's a function from R plus times Rn to Rn. And what is the ideal property of this enlargement? Of course, it should contain, for every parameter epsilon, it should contain the target set. Your target set is Tx. And when the parameter decreases, the accuracy of your approximation should improve. So in that sense, the size of your enlargement decreases when epsilon decreases. So these two are very natural. So the first one, it tells you that you have an enlargement, and the second one tells you that it is increasing with respect to epsilon. Now the third condition is the most interesting one, and it's fundamental to the fact of being an enlargement. The third condition is inspired on a basic property of the Epsilon Sub Differential. So again, we take our inspiration from convex analysis to obtain this condition. And what is the property of the Epsilon Sub Differential? The Epsilon Sub Differential has a fundamental property, which is called the transportation property. And the transportation property is a property that allows you to construct new elements in the graph of the epsilon subdifferential by means of known elements in the graph of the epsilon subdifferential or elements in the graph of the subdifferential itself. So it is important in terms of the structure of the graph. So what is the structure that we want to have in the graphs of these enlargements? And this condition, the third condition, which is called the transportation formula, is telling you what is the structure we are looking for. And it's also the step, it's also the link with convexity, with convex sets. I hope I will be able to tell you this in the few slides that are left. So what is this transportation formula? So you take two elements in the graph of this enlargement, and of course they have a domain epsilon 1 x1 and a domain epsilon 2 x2, and then you construct, by using an alpha, a convex coefficient, you construct the convex combination of both elements. In the elements in the domain x1, x2 give you some x hat, and the elements in the codomain x1 star, x2 star gives you some x tilde. And then you construct a parameter epsilon bar, which has the convex combination of the errors epsilon 1 and epsilon 2, plus a correction term. I won't go into the details, but the correction term is just the difference between the points in the domain minus the points in the codomain. So this correction term, you have to add it to the original convex combination of the parameters. And then the transportation formula requests that this epsilon bar should be non-negative. That's the first request. And the second request is that this convex combination of the images should be in the image through E, through the enlargement of the parameter epsilon bar times the convex combination of the domains. So this is the transportation formula. And convexity is so much inside this definition that this gives you the hint that there should be some nice connection with convexity coming out of this. Another observation is, and it's a consequence of the transportation formula, is that what happens when epsilon 1 and epsilon 2 are equal to 0 in this formula. If epsilon 1 and epsilon 2 are equal to 0, then this condition here tells me that E0 contains T by E1. So E1 says that it contains T. But moreover, if you take alpha, in fact, alpha strictly between 0, 1, and epsilon 1, epsilon 2 are 0, this part cancels. And this tells you that if this is greater than or equal to 0, because this factor here is going to be positive, then this means that this is going to be greater than or equal to 0. And this tells you that this map is monotone. And because capital T is maximally monotone, then this map should be exactly equal to T. So this is another consequence of these two definitions. So E1 and E3 imply that when you take 0 as the parameter, you recover the operator T. And in our analysis, we will always assume that the graph is closed, because if you have an E that satisfies these three properties, then when you take the closure of the graph of E, then it also satisfies these three properties. So you can always assume that you are working with closed graph mapping so that you preserve the outer semi-continuity property, which every maximally monotone operator already has, right? So we don't want to lose that property when we go to the enlargements. And a very a very important definition of enlargement corresponds to the epsilon subdifferential. So remember that the epsilon subdifferential is defined in this way. So out all those linear maps, such that when you compare the increment of the function from y to x, it's always above the increment of the corresponding linear function induced by x star. So when you have always this comparison for every y in the space, then your vector, your dual element x star is in the subdifferential. And the epsilon subdifferential tells you that if you relax this inequality by adding minus epsilon, then what you get is a larger set of vectors, and this larger set is called the epsilon subdifferential. And another tool that we are going to need is, okay, so if you have a convex function, then we assume also that the epigraph is closed. So we assume that our functions are what are called lower semi-continuous. And we assume that the domain is not empty. And the elements x that we take here are always in the domain of F. Right? Okay. And an example of an enlargement is for the case in which T is the subdifferential, then the epsilon subdifferential is a very nice example, also called the Bronsted-Rockefeller enlargement, is an example of an enlargement that verifies very nicely all these three properties. In fact, all these three properties were constructed by looking at the properties of the epsilon subdifferential. Okay, so I mentioned to you before that this is the Fenchel-Young system where equality with the scalar product holds if and only if you are in the graph of the operator. And then you can define the epsilon subdifferential just by relaxing the inequality by adding this epsilon. It gives you more slack, more flexibility, and then you have many more points that can satisfy this inequality, and those points are precisely those which are in the epsilon subdifferential. So this provides us with a map that goes from the enlargement to a convex function that verifies the Fenchel-Young system. And this tells us how we can travel from the subdifferential to the enlargement and from the enlargement to the convex function by taking this function here, the Fenchel-Young function. So this Fenchel-Young function characterizes the enlargement. Now we want to perform a similar journey, but instead of starting with the subdifferential, you start from an arbitrary maximally monotone operator T, right? And then we give an example of an enlargement of an arbitrary maximally monotone operator T, which I have shown you before, where if you would have 0 here, then this would be exactly equal to T of x. But if you relax it and you replace it by minus epsilon, you get a set that enlarges T of x, and this is called the epsilon enlargement of T of x, right? So for example, suppose that this is your subdifferential, the subdifferential that we have just seen. Then when you compute the epsilon subdifferential, and for this particular case, the epsilon subdifferential coincides with the epsilon enlargement. In general, they don't. In general, you have this inclusion. But for this particular function, both enlargements coincide. And the graph of the enlargement is precisely this example here. So if you take a point here, you can always approach via points in the graph of the enlargement, but not via points in the enlargement, in the graph of the original T. So this is why using a method that uses the epsilon subdifferential instead of the subdifferential itself gives you a better way of approximating every point in the graph. Here I should have said that TE, not T, but TE is an enlargement of T. And now, continuity properties, so every enlargement is automatically outer semi-continuous because we just take it in that way, we take the closure, and they are everywhere inner semi-continuous. So we have that property, and just wanted to show you again the Fitzpatrick function and the Fenchel-Young system, and this function characterizes the enlargement TE that we saw before. So in the same way, in a parallel way as the Fenchel-Young function univocally defines the epsilon subdifferential by adding the epsilon, if we add the epsilon but we use instead the Fitzpatrick function, what we obtain is the epsilon enlargement of T, right? And this is just a reminder of what is the Fitzpatrick family. So they are all the convex functions that verifies this Fenchel-Young system. And now we have that each of these, and as I mentioned before, each of these functions uniquely define the operator T. And now in these last two slides, I will show the connection with convexity. So how is this magic going to happen? So we take the graph of, we need to start with something which inherently defines our enlargement, which is the graph of E, the graph of the enlargement. And we make a change. We make a change. So remember that E goes from R plus times Rn to Rn. Therefore, in the domain, we have x tx, and we go to E of tx, right? So this means that tx comes first. So I have, in general, I will have t by u, where u belongs to E of ty, right? But I want to have t in the last coordinate because we want to generate an epigraph of some convex function. So we just define g tilde by putting t at the end. And then we define this function phi, which is a bijection. It's a bijection from Rn times R plus to the same set, defined in this way. So I just take xv, the same, the identity in the first two coordinates, and then in the last coordinate, I add the scalar product. And what happens is that for every point to set map, the satisfaction of the condition E3 is equivalent to the fact that the image of phi over this version of the graph, this permutation of the graph, is a convex set, right? So this gives you the connection with convexity. Now, moreover, the idea is to, given any enlargement E, you define the convex function lambda E as that unique function that has for epigraph this set phi of g tilde. And this is the last thing I wanted to show you. There is a bijective correspondence between every closed enlargement of T and every function in the Fitzpatrick family by this bijection. So this is the bijection I just showed you before. So the unique convex function whose epigraph is given by this map. And moreover, the inverse of this that goes in the opposite direction takes a function h and produces this enlargement, which is induced by h. And this enlargement belongs to the family of enlargements as long as h is lower semi-continuous and it belongs to the family h of t. So this means that every maximally monotone operator T not only induces a whole family of enlargement and also a whole family of convex functions, but each of these families are in a bijective correspondence. And I hope that I could pass you the beauty of this result. If I couldn't, it's not because the results are not beautiful, but it's just because of me. So thank you very much. And if anybody has more questions, please.
Thanks very much,
Go on.
Regina.
Thank you. So there is a question by Scott.
Yes, definitely. Scott, go ahead.
Well, thank you very much. I learned a lot from this, and I like this format of for the organizers. I like this format of having some of these tutorial type sessions because I don't ever want to stop being a student. I find it useful. I want to understand how. You talked about the advantage of an enlargement being that we gain this sort of inner semi-continuity where we can then take a sequence that is then approaching the point in the graph where we have 0 in the second coordinate. So what does that look like algorithmically? Like, how do we use these enlargements in terms of computation?
So let me show you. For example, suppose that you have a method in which you take a point. Okay, so now I want to have this. So you have Vk is in the subdifferential of xk, and uk is in the subdifferential of, okay, let's take the same points or different yk. So this is something that happens, for example, in bundle methods. But then what happens is that when you construct a bundle, for the bundle is a lower bound for your original function f, and you use this subgradient to construct the linear bounds, the lower bounds, and you take the maximum of those lower bounds. So in the end, what you will have when you combine this guy is you will have a wk, which is a combination of these guys. And this guy is not in the subdifferential of f at xk, and it's not in the subdifferential of f at yk. So you have to identify where is this guy wk. You know where this wk is going, but you don't know where. So you don't know what happens here, and you don't know what happens here. So what happens is that you can here take alpha xk plus 1 minus alpha yk, but then you are no longer in the subdifferential. Where are you? You are in some epsilon k subdifferential. And if you look at the convergence analysis of the bundle method, you will see that they very strongly use the property, the transportation property of this error epsilon k here. This epsilon k is some kind of error between the original function and the lower approximation. And you have to control this error epsilon k because it's very meaningful for the problem. You have to make it tend to 0. So the actual sequence that you generate is not in the graph of the subdifferential, but it is in the graph of the epsilon subdifferential, and it's that fact, the one that you use to show the convergence of the classical bundle method. That is the fact that Le Maréchal used in the proof, and Le Maréchal and Sagastizábal used in the proof of convergence. And when, together with Claudia Sagastizábal and Bernard Schweiter, we extended this to maximally monotone operators, we used again the enlargement we use that property of enlargement to show convergence.
Okay, so the bundle method, I understand, right? We take the max of these two, essentially these two hyperplanes that are generated by these points that are in the subdifferential, then sorry, where does the point W come from again? How did we determine that?
Okay, so this W somehow is a W that comes out from the algorithm. So
Okay.
it's a search direction. Let's put it that way. It's a search direction that arises during the bundle method, and that search direction is a combination of subdifferentials. It's a convex combination of subgradients at different points, because that's why the bundle method is called bundle, because you collect information while you go about, and that information gives you a better and better lower approximation. But as you go ahead, you collect more and more subdifferentials. And then I don't remember the technical details now, but I do remember that the subdifferential, that the search direction that you get is actually a convex combination of those subdifferentials that you collect into the bundle.
Yeah, I think what you do is you minimize the model function, don't you? And that's where you get the convex combination from, because you're minimizing the model function. Yeah.
Yes, exactly.
Yeah.
So your
Yeah.
model function is something like this, let's say,
Yeah.
right? And if you get the subdifferential at this point, then the subdifferential is going to be something that will be a convex combination of the subdifferential of here and the subdifferential at this point, right? Because you are combining them. And therefore, that, thank you, Andrew. So this is where this convex combination comes from.
Yeah.
Okay. Thank you. That was helpful.
You're welcome. You're welcome. There is something more here. Let me see. Okay. Who is Celine?
Okay. Any other questions? If not, I'm going to have a question just before we go further.
Yes.
I'm just wondering, Regina, I mean, I'm just thinking back into my early days of studying multifunctions, and one way in which people used to create an outer approximation that at least had a lot of continuous selections was just to kind of evaluate the function, the multifunction on a moving ball of a radius epsilon 2. And of course, that gives you a lot of continuous selections. It's useful in fixed point theorem. And I noticed with your enlargements that they seem to contain that multifunction, that's that particular enlargement, which really just fattens out the vertical jumps, by a ball. Is that a property of those enlargements in general, that they would contain that sort of evaluation of a moving ball?
Maybe. So if you are in the interior of the domain, I think that you may contain a ball if you are in the interior of the domain.
Yeah.
But if you are in the boundary, I mean, you cannot go beyond the boundary.
Yeah, you couldn't do that. You wouldn't be defined. Yeah.
If you are in the interior of the domain, you may be able to contain a ball. I think you're referring to the Goldstein enlargement.
Yeah. It does
the
come
Goldstein
up sometimes,
enlargement.
Yeah.
And I think that the Goldstein enlargement, I find it difficult to make the connection with convexity with the Goldstein enlargement. I think the beauty of this type of enlargement is that you can make such an elegant connection with the family of not only one convex, with a whole family of convex functions, right?
Yeah, and of course that the Goldstein enlargement is not in a semi-continuous. It just happens to have a lot of selections, which gives you something.
Yes.
Yeah. Rania, you got a question?
Oh, sorry. I know that the time is
Yes, we're going over time now. We might
not too much ask for Regina. It's a quick question, very silly. Regina, the computation of the enlargement of differential or operators tries to make easier the task of find the guys in these sets, right? There is some computational way to compute this enlargement without the previous knowledge of the operator. In fact, I mean, if you get a function, it is so easy computationally to find the guy in the epsilon sub differential. Is too much better than find the guy in the sub differential properly?
Well, I think that if you want to construct something, you need to start from something, right? So in this case, the condition E3, so this transportation formula, I think it gives you a way of constructing elements. And even if you don't know the enlargement, you can construct the elements in the graph of the enlargement by using elements in the graph of T. And this is quite useful, in fact. So this is very useful. So you're right. I mean, computationally, when you have to go down and compute these things, it may not be so easy. But I think the main usefulness of this definition is that it gives you a way in which you can say, you can generate a method in which the iterates are constructed in such a way that you can say, I know that my iterate, like in the bundle method, I know that my iterate is, I know that I have two iterates in the graph of the subdifferential, and I know that if I combine them in a convex way, I can get a new element in the graph of the enlargement by this way. So this tells you what you can say about a guy that you already have, right? So about some situation in which you already know that you have two guys in the graph.
Yeah, I see.
Well, I'm quite conscious of the fact that we're getting over time here, but maybe just one last question from Julian, and then I think we might have to wrap it up. You're muted, Julian.
I'll try to be quick, sorry. First of all, thank you, Regina, for both presentations. I think they were really quite nice. And although I did notice a mistake at the beginning of your talk, when you said that you're a bad teacher, I think this was not right.
I am.
Is there, I have a feeling, especially at least in the convex case, that there's a relationship between epsilon, or between enlargement and smoothing. Functions. So, you know, can you, is there some way of maybe going towards what Rennie asked? Is there some way of approximating or evaluating the epsilon sub differentials from smoothing functions of some sort?
That's an interesting question, but what I can say is that it is a fact that even if the maximally monotone operator T is not inner semi-continuous, all the enlargements are. So the enlargement is a point-to-set map. So in the sense of continuity of point-to-set maps, producing the enlargement is automatically producing a better version of T, in the sense that it has these two very nice continuity properties. So I did not mention here, but you can even show that the enlargement is Lipschitz continuous in the point-to-set sense, which is much, much stronger than inner semi-continuity. So I didn't want to go into the technical details here, but the enlargement is inner semi-continuous. And yes, it would be interesting to approximate by using, maybe adding some specific functions to a given function and then producing enlargements. I don't know. I haven't thought of that, but I think it's an interesting way to go in terms of smoothing, for example.
Right. Yeah. I was thinking maybe of some kind of boundary of your, yeah, I don't know. Anyway, yeah. Just, yeah. Thank you.
You're welcome.
All right. Well, I think we better wrap it up now, because we all need a little break to go and get a little bit of lunch or something like that before we reconvene. So I'd like to thank Regina again for two really lovely presentations, and we will reconvene in about an hour. Well, at 3 o'clock, I guess, is when we're reconvening. So thanks very much, Regina, again. That was very nice.
Thank you, and thank you to everybody for being so patient with me. I see you soon then in the afternoon session. Bye-bye, everybody.
Thank you very much, Regina.
Thank you very much, Regina. Very
Thank you.
Bye,
Thank
guys.
you very much. Bye-bye.